Now that we have a clear structure for the likelihood function that we will be using, and we have prior distributions for all of our parameters, we can proceed to derive the posterior distribution that we will be working with. So we want to write down the joint posterior distribution. And that joint posterior distribution includes, of course, the weights and the parameters of each of the components, but it also involves the vector of indicators C that we have introduced to simplify the structure of the likelihood. And by definition, this quantity is proportional to the distribution of the data given all the parameters multiplied by the distribution of the missing data parameters given omega and theta, multiplied by the prior distribution on the parameters, multiplied by the prior distribution on the theta. So this is the general expression, the general form for that posterior distribution. Now, we have already seen what the form of these different terms is. In particular, this joint distribution of the data can be written as a double product, first over components, and then over the groups of observations that belong to each one of those components of G sub k, x sub I given theta k. So that is the first piece that we're interested in. The second piece, we have already seen also how to write it down. This is going to be the product from k equals 1 to capital K of omega sub k sum of the indicators of C sub I is equal to k from 1 to n. This is our second piece. Then we discussed using a Dirichlet distribution for this. So ignoring some proportionality constants, this becomes the product from k equals 1 to capital K of omega sub k raised to the a sub k minus 1. That's this piece. And then finally, we're going to have another product. So typically, we use independent priors for each one of the theta k's. As I said, we'll typically try to pick them so that they are conjugate to this kernel G sub k. But for now, I'm going to write it in general form by writing this as P sub k of theta. Okay. And that's what the last term in the expression is. So we have written down a full expression for this. Now, it should be more or less clear how we need to proceed. So we need full conditionals for all the parameters in the model. In particular, we are going to need a full conditional for omega given all the other parameters. We're going to need a full conditional for each one of the C sub i's given the rest of the parameters. And we're going to need a full conditional for each one of the theta k's given the rest of the parameters. And so to derive these full conditionals, what we will do is we will pick particular pieces from these expressions to retain and to construct these particular full conditionals. Let's proceed now to derive each one of the full conditionals that we need to derive a Gibbs sampler or a Markov Chain Monte Carlo algorithm for this problem. Let's start with the full posterior distribution for the weights. And please note that we're going to work with all the weights as a block. So we're going to try to sample them all together rather than looking at each one of them at a time. So this full conditional distribution is made up of the terms in this full posterior distribution that involves omega k. And if you look at this expression carefully, you will see that this piece doesn't depend on omega k in any way, and that this piece doesn't depend on any of the omega k's either. So it's just these two pieces in the middle that we need to consider. Furthermore, the two pieces are very similar, so both involve products over k of the weight raised to some power. So we can actually combine the two expressions together and just write them as the product from 1 to capital K of omega sub k raised to the sum of these indicator functions plus a sub k minus 1. And this looks exactly like the prior that we used, except that now we have updated parameters. So I could write this as the product of omega sub k raised to the a sub k, call them stars, minus 1, where a sub k star is just the original a sub k plus the sum from 1 to n of the indicators of c sub I equals to k. So just doing this little change makes it very clear that the form of the posterior is exactly the same form as the prior. In other words, this is a conditionally conjugate prior for our problem. And that just means that omega is going to be distributed as a Dirichlet given all the other parameters, but with these updated parameters a1 star all the way to a k star. And this is very interesting because essentially a posteriori we know that the expected value of omega given all the other parameters, so this is the expected value of the full conditional, this is not the expected value of the marginal posterior, but this is the expected value of the full conditional. That is going to be a sub k star divided by the sum from L equals 1 to k of a sub L star. But this is just a sub k plus the sum from 1 to n of these indicators, c sub I equals to k, divided by n plus the sum from L equals 1 to capital K of the a sub L's. And n just comes from the fact that if I sum over all the components, then the sum of those values is going to be n. So this is just the number of observations that are currently assigned to the case component. And if the values of a, k are small, then this is just roughly speaking, so approximately the proportion of observations in component k. And this has a very nice analogy with the computations that we did in the EM algorithm. If you remember, the way in which we computed the weights in that case, or the MLE for the weights, was by essentially computing a quantity that could also be interpreted as, roughly speaking, the proportion of observations in that step of the algorithm that were assigned to that component. So this provides a mirror image to what we did with the EM algorithm, but that has a Bayesian flavor rather than a frequentist flavor. Let's continue now with the posterior distribution, the full conditional posterior distribution for the indicators, for the C sub i's. I'm interested in the probability that C sub I is equal to k given the data. As before, this is going to be proportional to just the terms in this large product that depend on C sub I. And if you look at it carefully, C sub I only appears in these two terms of the product. This have nothing to do with C sub I. And in particular, it appears in a single term within this really large product and in a single term within this product. So the term that depends on C sub I being equal to k in here is omega sub k. And the term that depends on C sub I equal to k in here, it's just G sub k of xi given theta. Okay. And this is true for every k from 1 to capital K. Remember that C sub I is a discrete random variable taking values between 1 and k because it indicates which component generated the observation. So if I want to get rid of the proportionality sign and actually being able to write what the probability is, I just need to normalize this by dividing over the sum of these quantities over k. So that means that P of C sub I equals to k, given all the other parameters, is equal to omega sub k, G sub k, x sub I given theta k divided by the sum from L equals 1 to capital K of omega L G sub L of xi given theta L. And if you look at this expression carefully, you will realize that it is very similar to the expression that we use when computing in the EM algorithm, the weights associated with each one of the observations. In fact, it is the same expression, and this is just what we called in the EM algorithm BIK. Finally, let's consider the full conditional posterior distribution for the theta case. So we need P of theta k given all the other parameters in the model. Again, we just pick from this whole product the terms that have to do with theta k. In this case, it is the two in the middle that do not depend on it. And within this big expression, we just have a few terms that contain theta k, and those correspond to the observations that are currently assigned to that particular component. So this expression is proportional to the product over the i's that have been assigned to the case component of G sub k, x sub I, theta k. And among this product, again, there is a single term that belongs to theta k. So the form of the full conditional posterior distribution for the parameter theta k is simply this. Now, without a specific choice of G and P, it is hard to write to further simplify this expression. But what I do want to note here is that if this prior P sub k is conjugate to this kernel G sub k, then we typically know what family this posterior distribution will belong to. And that will make computation much simpler because you will typically be able to sample from that full posterior conditional distribution in using a direct sampler. This will become a little bit more clear once we do an example with mixture models, which is what we're going to do next.